Okay, let's get started. Welcome to our inaugural PM webinar. This is the first of several webinars in the coming weeks and months that Centrus will be hosting with the intent of educating our customer base on powder metal and how the applications are best suited to powder metal and what Centrus ultimately can do for you. I'd ask that anyone hold their questions to the end of the call. I will mute everyone's line to reduce feedback. And if you want to ask a question, please go ahead and input it into the chat box, and we'll do our best to get back to you with a response. Today's agenda, we're going to do an overview of Centrus, a very brief overview of Centrus, just to inform you as to our size and scope, as well as basic coverage of Powder Metal 101. We're going to explain what happens with powder from the powder metal arrival at a facility to the process of pressing, sintering, any secondary operations, and a finished product. And then we're going to talk about why choose powder metal. We've broken this down into 4 guide points, or a 4-point guide, 4 differentiators for powder metal, why you would choose it, and what's best suited to powder metal. And then we're going to answer any questions. We're going to give you the opportunity to propose questions to myself or to Rick Armstrong, who is also online. Well, welcome to the webinar. I'm Phil Goodwin. I'm the president of Centrus. With me online is Rick Armstrong, our manager of sales and applications. Together, we have over 65 years of powder metal experience. In addition to that, we have a significant staff with a combined many hundreds of years of experience in powder metal. Welcome to Centrus. Centrus was founded in 1972 by Centrus of Italy. Primarily, we're serving the automotive, industrial, and consumer markets and the global market, shipping all over the world. We offer manufacturing from the raw material to finished products, including captive secondary operations and assemblies in a 40,000 square foot facility with 100 plus employees. Now, Powder Metal 101. Let's talk about the powder. Base materials in powder metal include iron, copper, nickel, aluminum, titanium, and combinations thereof. Traditionally, in our facility, for example, we operate in iron-based materials, whether it be steel alloys or what have you, or even stainless steel alloys. And then there are alloys, of course, steel, stainless, brass, bronze. We conduct pressing of bronze bushings and what have you, very common in powder metal. And then there's the opportunity for composite materials, where you combine metallic and non-metallic base materials. This is a fairly new area of powder metal, and there are opportunities in that area. Typically in our facility, we've combined metallic alloys, for example, in a hybrid application, a component that was 50% stainless steel for non-magnetic properties, and 50% magnetic iron, or an iron that's actually designed for magnetic applications with a high propensity for magnetic transmission. In addition, there are lubricants. And lubricants can be an additive in the material, and generally are, for ejection from tools, as well as carbon in the form of graphite, and so in some cases organic compound, which could be used for strength during the pressing operation, or other binder treatments that can add to strength of the material. The picture you see is powder being poured for measurement of flow, which is an important characteristic of powder as it enters the cavity to be pressed into a final component. And later in the year, we're going to host a detailed webinar on powder production and alloys that will be in conjunction with one of our major suppliers, and you'll get to understand how powder is made and what perhaps alloy selection may be best for your application. Powder is fed typically in compaction by gravity. In other words, through a tube at the back of a press. The powder is fed into a cavity, and then it is pressed at a tonnage or a pressure of 35 to 45 short tons per square inch. And in the case of the example of the picture, it's a 200-ton press that is being used for component pressing via this delivery method. There are also ball screw feeder methods which could feed powder in a similar fashion without the necessity for gravity. However, gravity is the most common feeding method. 35 to 45 short tons is actually about 482 to 620 megapascals for those of you who deal in metric. In powder metal, parts have a small amount of lubricant to enable extraction from the die. We talked about that in the previous section. And that basically is in place to allow the part to eject from the die cavity without causing damage to the die or the tools, or certainly reducing significantly that. Normally it's in the form of 0.75% acrylax or a zinc stearate material. Moving to sintering. Sintering involves three primary stages in a reducing atmosphere. The atmosphere is one of hydrogen-nitrogen in combination, N2H2, or a reacted, endothermic reacted natural gas to create an endothermic gas that is used as a protective atmosphere. The purpose of the atmosphere is to eliminate the potential for oxidization at the surface of the part once the part reaches high temperature. There are three stages, as I said, to sintering. One removes the lubricant. The initial stage removes the lubricant from the part, which could inhibit the process later and cause various ugly characteristics such as bubbling and what have you further in the process. So you remove the lubricant and begin to heat the part to temperature where it enters the high heat zone. The part's then exposed to a temperature of 2050 Fahrenheit or 1120 degrees Celsius for approximately 30 minutes to form what's called a sinter bond. And in the sinter bond, what happens is the material, every particle has an outer layer that is effectively an iron oxide. That's reduced and allows then the formation of a sinter bond between the particles underneath. In other words, what happens is the particles effectively glue themselves to each other. That's the sinter bond. The sinter bond then, when it's cooled down in the cooling zone, effectively creates that solid metal part, very similar to a raw material. Secondary finishing, the next step in our process. The main benefit of powder metal is the ability to produce a net or near net shape with minimal waste. Further processing can take place in the form of CNC turning, milling, grinding, drilling, those types of activities in order to achieve some of the tighter tolerances, perhaps on the order of significantly less than 50 microns or a thousandth of an inch. That can be done within certainly sinterous operations. Additionally, parts can be subject to secondary steam oxide coatings. We talked about pot steamers were mentioned on the prior slide. This adds a steam oxide coating, which adds a level of rust inhibition as well as hardness characteristics for some wear applications and for the addition of, in some cases, coatings that are used that are done outside our facility and by third-party coaters for applications such as high heat needs up to temperatures in excess of 1,000 degrees Celsius. For example, we've made plates in the past that have had materials that have actually been used on the space shuttle when they were on re-entry to prevent burn-up in the atmosphere. As well as through hardening. Through hardening can be conducted to allow parts to have strength and wear characteristics as required, up to around Rockwell C35 apparent hardness and say 58 particle hardness. Further in secondary finishing is subassemblies. It's always possible to take that component and assemble something else to it. This is something that we do at Centris and that can be done in the powder metal operation. You can add other powder metal components to it by methods of attachment. Assembly can also be conducted during the sintering process. You can have two distinct materials where a sinter bond is formed between the two components that would be assembled together, and then you'd have a high growth component with a higher shrinkage component that would allow it to basically lock tight. You can also conduct brazing, and certainly PM is used in welding, friction welding, and various types of CD welding and what have you. And in summary, we've covered PM from the powder stage through compaction. Again, a fairly brief introduction. However, we have covered that through that stage. We've also talked a little bit about sintering, and we briefly introduced some of the extensive secondary operations capabilities that exist for fine, tight tolerancing of components should that be necessary. So, the PM advantage. What is the PM advantage? We've broken PM advantages down to four basic distinct characteristics, or four distinct categories, I'm sorry. Cost, strength and durability, design flexibility, and the complete solution. Some of the first powder metal advantage, cost. PM offers minimized waste. It's a recognized green technology where all powder is either sourced from scrap, that's iron scrap, or waste metal that can be readily recycled as powder. In other words, during the pressing operation, if you have waste material, that could be readily recycled back into powder by a powder blending facility. They can take that powder and, if necessary, regrind it down to its smallest form and then blend it back into another mix and allow for that reuse. Or ultimately, if parts are sintered, in other words, they become that solid part that we discussed earlier, that component can then be sold to scrap metal dealers, which could be molten down and then could be used to create a water atomized powder, which again becomes powder for reuse later on in the industry. And this is typically what takes place. In addition, there are other examples where, for example, one of our suppliers mines titanium as a practice. Titanium is found in iron ore. The iron ore is a byproduct of that process. In other words, it becomes a scrap from the titanium mining process. The iron ore is then taken and then trimmed and balanced for use as powder and then water atomized to become powder, which is then used further in processing by powder metal manufacturers. The powder metal advantage, strength and durability. Materials can be used that are not otherwise feasible with our ability to offer customized alloys. In other words, you may not be able to generally make a material. It may not be available on the market. However, in powder metal, alloys can be created by the combining of constituent materials. In other words, you could take a base iron powder. To that iron could be added perhaps copper or nickel or both. Molybdenum, various other alloys could be added to that in order to create the characteristics that are best suited to your application. This is something relatively inexpensive in terms of capability within powder metal. And these alloys can be created by a pre-alloying method, which means that the alloy is actually introduced at the creation stage, or later on can be mixed. For example, in many cases, the standard mix of iron, copper, carbon, which is typically an FCO208 designation under MPIF, is something that means it's 2% copper and 0.8 carbon, and the balance is really made up of iron, and then there could be some other constituents added to that. So what do you get from that? Well, you get greater durability. You also get improved wear. You get improved strength. Other characteristics are possible. The next powder metal advantage, design flexibility. Complex forms, such as the gear that you see before you, are relatively easily manufactured with powder metal. As long as the pressing is in the axial direction, up and down. It has to be a vertical pressing motion in general. Now, there can be characteristics that are imparted by secondary operations such as milling, which can be done also in the green state, or by turning or what have you. But typically, a powder metal part is made with a vertical pressing motion. What you see before you is a gear. Those gear teeth were formed during the pressing activity. In other words, there was no hobbing of these teeth. In standard material manufacturing, if you were to use wrought material to produce these two components, what you find is that you'd have to make a round part, probably by forging or extrusion or casting or what have you, and then you would hob the teeth into those parts. In creating the hobbing process, you allow an increased possibility of variation due to material failure, insert failure, however the tooling is used, could create variation between the parts. In powder metal, the uniformity of the teeth is determined by the die and tool members. And these are very tightly controlled tolerances, usually in the 1/10,000th of an inch tolerance range, that are used to press components. Further, if you look at the inner diameter of the inner gear, that has two lugs on it, which are actually something that would, in standard wrought material, perhaps be created by broaching or another more expensive process. So this is something that's inherent in powder metal. A gear is a good example, albeit an older one, of where powder metal finds its best suited applications. Now, further to this, that gear, by the way, could be a Class 6, Class 8 AGMA scale gear. Further to this, the key really, and we find this in Sinteris particularly, is that the earlier that we get to the customer to discuss the manufacture of this part, to discuss the application, the more likely we are to not only save money, to make the product more robust for powder metal manufacturing. There are certain characteristics that are best suited to powder metal, and we can probably save money and time, certainly, by looking at that design early in the stage of manufacture. In other words, when the customer gets a print, if the print's not locked down, it gives us the opportunity to go in and make the part better for powder and usually less expensive for that customer. The final powder metal advantage, complete solutions. We see cost savings in powder metal as a result of labor because of the fairly large output numbers, from scales to several million pieces from 1,000 pieces. Certainly, the technology allows different activities to take place with the powder metal, be it secondary finishing or be it surface treatments, those kinds of things. Productivity, you have productivity and output improvements. In other words, you get very large output for the relative input. Further to that, there are, as you see there, support in terms of design and engineering, allowing us to better design that part early in the process to make it meet the powder metal requirements. And finally, you talk about reliability, and this may tend more towards Sinteris. However, we are TS 16949 registered, and have been QS prior to that, and ISO prior to that, meeting global standards for quality. We also have a compliance to VDA 6.3, the German standard, which is something that is audited by several customers, so we maintain a system that is compliant with VDA 6.3. The goal obviously being to meet or exceed the end-use customer's requirements. And finally, the delivery options, you see, it's cost competitive. Our location is close to, in case of Sinteris, close to major highways, and shipping all over the world from where we are, shipping to Mexico, to the U.S., within Canada, to Europe, to China. We've shipped to India. There's a variety of options available, and cost is not quite as high as one might think. As well, powder is readily available, supplied on a can-ban basis by our powder supplier. We maintain a large supply at their location for short order requirements. So best fit applications. What are the best fit applications? examples you see are fairly complex shapes. The one on the left is actually an excellent powder metal example. It has very little secondary operations conducted. It does get heat treated outside with a through hardened process. However, in addition to that, there is some slight grooving that's conducted with secondary machining, and also a honing of the inner diameter. But there's a good example where gear teeth have been formed, and the part basically resembles what it looks like from the early powder stage or the briquette stage, and looks like that as finished. The next example is one of an assembly of smaller components that can readily be done. This can be conducted in our facilities and certainly at customer facilities with products supplied by us. Those are sinter hardened components. Sinter hardening is a replacement method for through hardening that can be conducted internally and yields a much cleaner part than you might see from a through hardened oil quench. And that is also, from an environmental standpoint, cleaner, less use, less reliability on oil for that quenching operation. And then the final component you see on the screen is actually part of a bearing assembly for a journal bearing assembly for a cotton picker. This uses many operations that are really pushes the extent of what's available in powder metal. As seen, that part couldn't be pressed. However, there's a green milling operation that takes out a material along one of the tabs. There's hard turning, there's soft turning, there's drilling, there is honing. This component sees a lot of activity, as well as through hardening externally. And this component sees a lot of these activities. It's a good example of great use of powder metal technology. So, best fit applications: automotive components and subassemblies, industrial agricultural components and vehicles, and consumer goods. You might not think of it, but every car has 60 pounds of powder metal, roughly, that you see on the road, whether it be in the form of carriers, or gears, or sprockets, bases, hubs, those types of things, brake components. And then there's industrial applications such as pumps, pump gears, pump plates. There's a lot of industrial applications out there. And in the consumer goods applications, you could take consumer goods, it could be part of agricultural vehicles. There's a lot in farm equipment, tractors, those types of things have a lot of gears and components made out of powder metal. And hand tools, for example, lock nuts, chuck components, things like that, that are made out of powder. And then what's next? What's coming up? What are the best fit applications moving forward in powder metal? 3D additive manufacturing. Additive manufacturing is effectively what you've probably all seen. 3D printing. You see plastic parts that are printed in a 3D printer. It's all over the television. It's everywhere in your life that you see people talking about it. People can buy a desktop 3D printer for home. The next level of powder metal technology is actually additive manufacturing, using a similar powder method, printing by layers and sintering as the process goes. In other words, what happens is the sintering takes place often by things such as laser as the powder is layered onto a component, resulting in a near net part by the end of the process. What you see before you are some very complex forms. Joints for hip replacement, for example, are now being manufactured by this method and require some external finishing, but they offer some significant improvements in capability. And for example, the matrix that could be created whereby the material can allow the growth of organic muscle and tissue to mesh with the material. And this is made by means that would not be possible by any other method. Gear forms with complex matrices in the center, as you see in there. Complex turbines and rotors. And again, a good example of something that could be printed is the glove and ball on the right, which is a complex matrix of components. And these things can all be printed. This is the latest in technology for powder metal, and this is the direction in which powder metal is heading for some applications, particularly specialty ones. And it's a direction that Sintris hopes to venture into in the very near future. And we will be presenting information on this at a later date in another webinar. If anyone has any questions or comments, please do so now. We'll answer those. We'll do the best we can to answer them. Rick Armstrong is also online. If you have any questions, please leave them in the chat box, or feel free to ask the question at the conclusion of the webinar. And finally, I'd like to thank you all for attending. Is the powder metal advantage right for you? You can determine that with our assistance. We'd be happy to visit with any of you. Please don't hesitate to contact us. Our sales group will follow up with you to ensure that this webinar met with your expectations, and we're more than happy to work with you in the future to develop that powder metal advantage. Thank you.